Hey guys, so I'm really sorry that I didn't get anything posted yesterday. I'm sure you guys are so interested in the whole saga as to why I didn't, but I feel like I owe you an explanation because I always get everything posted, and this is the first time I didn't. So the short version is earlier this week I had tried to post notes for one of the other classes, and I got through the whole note session. And when I went to check the recording, turns out that the computer had recorded the video of it and no sound. And I spent about 3 hours going through the settings and reading forums about the program that I was recording on and messing with the computer and the program, and nothing worked. So then I restarted the computer and I re-downloaded the program and spent the whole day and many screaming sessions trying to figure it out and re-recording the notes, and at any rate, essentially doing what I did to you guys, not getting anything posted for the class and having to post it the next day. By the time I finally figured out what was wrong, I actually never figured out what was wrong, but I had restarted the computer, re-downloaded the program, had to re-record everything, and yeah, so what happened yesterday, I finally figured out. I watched the recording, everything looked fine, but then when I tried to upload it to YouTube, it wouldn't upload. So what I finally figured out after lots of frustration yesterday, apparently the program was recording it in a weird file type that wouldn't upload, and I could not figure out not how to fix that, but I could not figure out how to change the way it was recording it. So at any rate, it should work this time. Hopefully. Won't be able to figure that out until after I record it, so we'll see. At any rate, let's get started. So this is actually two articles. You can see here. The first article is a news article, and it's about the Yellowstone supervolcano, and what the seismologists, and those are people who study earthquake activity, what the seismologists are looking at is how to use earthquake waves to study the Yellowstone supervolcano. So I thought that was really cool. And using this recording program, which has brought me so much frustration, but it is a cool program. You guys can actually see me doing the read along, but you can also see the article, which I thought was really cool. So anyway, let's get started. All right, so the title of the article is Yellowstone Earthquakes Reveal a Volcanic System 6 Times Bigger Than We Thought, which is really scary because they are predicting that the Yellowstone supervolcano is going to erupt at some point and destroy life on this planet as we know it. So that's terrifying, especially if it's 6 times bigger than we thought it was. At any rate, let's start reading. So seismologist, which, like I said, is somebody who studies earthquake activity. Seismologists have discovered a massive magma reservoir. And remember, when we talked about volcanoes, we said that magma reservoirs are that place under the volcano, that like magma chamber is what we called it, but it's the same thing. That's that spot under the volcano where the magma sort of chills until the volcano erupts. All right. So seismologists have discovered a massive magma reservoir beneath the Yellowstone supervolcano in Wyoming, U.S., that suggests its volcanic system could be more than 5.6 times larger than was previously thought. So again, a little terrifying. Although it was already known that Yellowstone had one magma reservoir located about 5 to 16 kilometers, or 3 to 10 miles, below the surface, the new study, published in Science, has revealed another, much larger reservoir sitting directly below the surface, located around 20 to 50 kilometers, or 12 to 30 miles, below the surface. This reservoir is thought to have a volume of around 46,000 cubic kilometers, compared to a volume of around 10,000 cubic kilometers for the shallow reservoir. So yeah. So originally when they first were talking about the Yellowstone supervolcano erupting with that original reservoir of the 10,000 cubic kilometers, they were talking about that sort of destroying everything. And now they're saying there's a second reservoir that, if you look at that, that's 5 times larger. So that's a little scary. To make their discovery, scientists analyzed the vibrations made by earthquakes that passed beneath the volcano. The technique not only sheds light on this volcano's potentially life-threatening eruptions, but it could also help us understand other volcanoes, such as Calbuco, which is currently erupting in Chile. Okay, so in other words, we can use this for Yellowstone, which is useful, but it's not just for Yellowstone. So in other words, we can use this for any erupting volcano. Kind of cool. So I love that. I love that picture. It's gorgeous. I mean, it's also a dangerous volcano, but gorgeous picture called Sleeping Beauty. All right. Yellowstone volcano is composed of an immense volcanic crater known as a caldera. Hopefully we remember that. More than 70 kilometers or 44 miles in length, most of which lies within Yellowstone National Park. If you've been there, I've never been there, but I've seen pictures. Oh my God, I would love to go there because the pictures are beautiful. The volcano rarely erupts lava. It last did so about 70,000 years ago, but the magma lying beneath the surface gives rise to spectacular geothermal features, such as geysers and colorful hot springs. So geothermal, geo meaning earth and thermal meaning heat, means that you get heat coming out of the earth. So geysers would be water shooting up, and hot springs would be just literally like pools that are hot. The last large eruption at Yellowstone was 640,000 years ago and ejected around 1,000 cubic kilometers or 240 cubic miles of volcanic material. That is a crazy amount of lava. If we think about, so that, I mean, honestly, that number in my head is, that's an insane amount. Because like 1,000 cubic kilometers. I mean, just like a cubic meter is a large amount. Like a cubic meter is a lot. And 1 cubic kilometer is, I mean, 1 cubic kilometer is more than enough to like cover a good amount of Haddon Township. And then we're talking about 1,000 cubic kilometers. Like that's a crazy amount in my head. Okay. This cataclysm created the Yellowstone caldera. To get an idea of the scale of this, the largest eruption in recorded history, Mount Tambora in 1815, erupted about 1/6 of that. Now, they're saying recorded history, meaning the Yellowstone eruption 640,000 years ago, that was before there were humans, so we weren't recording that history. The reason we know it happened is because geologists and seismologists can look at the rocks, and they can look at they can look at the rocks, and they can look at the seismic activity that they're seeing, and they can basically date that and say, okay, it happened about 640,000 years ago, but there's no recorded history to say, well, there were people there. Yes, this happened. So that's what they're saying. Magma reservoirs are thought to occur beneath most volcanoes and play a crucial role in the dynamics of eruptions. However, they are too deep and conditions within them too extreme to be measured directly. So volcanologists, those aren't people from Star Trek who study Vulcans, by the way. Those are people who study volcanoes. Shh. Apparently my cat wants to help. So volcanologists have to infer information about them using other means, such as measuring seismic waves. That's why we're here today. These waves travel more slowly when they pass through molten rock, and accordingly, the groups were able to use the velocities of the earthquake waves to infer the presence of a large, deep zone of partially molten material. Okay, so what they're saying there is that these waves travel slower through molten rock or slower through liquid than they do through solid rock. So in other words, we want to take our knowledge of chemistry and our knowledge of physics and sort of put them together. So we're going to talk about waves, and we're going to talk about solids and liquids here. So our knowledge of waves is going to allow us to talk about these seismic waves. And our knowledge of solids and liquids is going to allow us to talk about why these things might travel faster in a solid but slower in a liquid. So why might these things travel faster in a solid and slower in a liquid? Well, solids have very, very tightly packed atoms and molecules, right? But liquids, they're a little bit further apart. So in a solid, because the waves require the movement of energy, remember that's what a wave is a movement of energy. So because the wave requires movement of energy and the solid has very tightly packed atoms and molecules, all that has to happen in a solid is, because the atoms and molecules are very tightly packed, those atoms and molecules don't take very long to just bang into each other. In a liquid, because the atoms and molecules are just a little bit further apart, it takes a little bit longer to bang into each other. So that means that in a liquid, like magma, the waves are going to travel a little bit slower. And that can be detected by somebody who's studying those waves, like a seismologist or a volcanologist. There's a little bit of crossover there. So those people can actually detect the change in velocity, and they can tell what's solid rock versus liquid rock. All right, so let's look at carbon footprint explained. So this is a picture of a geyser. Kind of cool, right? So it's actually just like all this water just shooting up out of the rock. Dangerous to stand near, but really cool. So the magma stored in the deeper reservoir probably won't cause eruptions at Yellowstone directly. Instead, it likely acts as a feeder for the smaller, shallower reservoir. So they're saying that deeper reservoir like pushes magma up to that shallower reservoir. So that deeper reservoir isn't actually going to cause the eruption itself. It's going to push magma up to the shallower reservoir. And what I'm thinking, now I haven't gone through, I'm thinking that shallower reservoir then is going to build up pressure because more magma is getting up there, and there's only a certain amount of room there, right? So more magma is getting up there, and then eventually there's only so much room, there's going to be pressure built up, and it's going to blow. Okay, which is the ultimate source of the volcano's catastrophic eruptions. Scientists had suspected the existence of a second magma reservoir at Yellowstone for some time, but this new evidence is among the strongest support of the theory to date. The discovery of this second magma reservoir may also help to explain a mysterious feature of the Yellowstone volcano, its carbon footprint. Carbon dioxide gas is commonplace at volcanoes. It's given off by rising magma. But Yellowstone's output, which is around 45,000 tons of carbon dioxide each day, that's a lot, was too high to be explained by a single magma reservoir. But according to the study's authors, the presence of the new reservoir is enough to account for the volcano's carbon dioxide flux. So what they're saying is, this molten magma that's in most volcanoes gives off carbon dioxide, and the amount of carbon dioxide given off can tell these volcanologists how much magma is down there. It's one of the ways that they study these magma reservoirs. And they were suspecting that there was something going on, probably a second magma reservoir in Yellowstone, because they could tell that there was not enough magma down there to explain the amount of carbon dioxide coming out of Yellowstone's volcano. So the discovery of this secondary magma reservoir explains the amount of carbon dioxide coming out. So kind of cool. This is an awesome picture, by the way. This isn't Yellowstone. You can see in the caption, this is the eruption of Calbuco in Chile. But that's such a cool picture. Just when photographers capture stuff like this, it blows me away. This is so cool. If the high-resolution seismic imaging technique used in the study could be repeated at other volcanoes whose deep structure is poorly understood, such as Calbuco volcano in Chile, volcanologists might eventually be able to understand how such eruptions take place. The first stirrings of volcanic eruptions happen far below the surface. If researchers can emulate the findings at Yellowstone at other volcanoes, it can only tell us more about the risks they pose. So what they're saying there, and that's the end of the article, so I'll scroll back up. So what they're saying there is that Calbuco in Chile, they don't know much about what's going on underneath. So there's a magma reservoir there, but they don't really know how large it is, or if there's one, if there's two, like what's going on. So they don't have enough information about Calbuco to talk about much about like what's going on and predict eruptions there. Considering people live there, it would be nice to be able to predict eruptions. So if they can use this technique there, they'd be able to predict eruptions and hopefully save lives, honestly. So I'm going to go to our second article and read a little bit about seismic waves so that we have a little bit of information about those and we can hopefully understand a bit more about what they're doing. So let's look at seismic waves. All right. So this is going to talk about seismic waves and the different kinds. Seismic waves come in different flavors. When Earth begins to rock and roll and shimmy, it's important to know what the various types of shakes mean. Okay, so the caption of the picture says there are several different types of seismic waves, some of which are more damaging than others. All right. Earthquakes and underground explosions can release a lot of energy. That energy ripples away from its source in a variety of ways. Some of those vibrations will move forward and back through the material they travel through. Other waves travel just like ocean waves, where they make the material they pass through move up and down compared to the direction the wave is traveling. And while some of these waves travel deep within the planet, still others move only along the surface. Studying where these various flavors of waves are and how they move not only can help scientists pinpoint where an earthquake or explosion occurred, but also can shed light on the structure of our inner planet. So, here's the thing. Some of that seems like maybe it's not important, but it actually all is important. So, when we talk about where an earthquake or explosion occurred, that might not seem important in the moment, but here's why it is. First of all, yes, when we're talking about like the EMTs and the firefighters who are going out to save people's lives, is it important to them where the earth, like to pinpoint where exactly the earthquake occurred? Maybe not. They're going out to save people's lives. It doesn't matter to them where exactly on the tectonic plate the earthquake occurred. So no, for them, maybe not. But for the seismologists, it's very important to pinpoint where exactly the earthquake occurred, and here's why. If they know where exactly the earthquake occurred, they can tell if that's the beginning of the earthquake, if that's the earthquake itself, or if that's the end of the earthquake. Because the thing is, earthquakes happen in waves. Earthquakes happen over time. So we talked about transform plate boundaries, right? So transform plate boundaries happen earthquakes happen at transform plate boundaries when they kind of catch on each other and there's a snag and then they kind of like rip past each other. Well, when that happens, an earthquake can happen, like it can be kind of small and it's just like one little ripple. Or if that snag kind of builds up and there might be like a little shake here and that's one little earthquake, but if the seismologists know that's a little earthquake, but here's the thing, that's still pushing. So if they know that this point is where that's happening, then they know that, hey, there's going to be another big earthquake coming. So if they can pinpoint that that's where it's happening, then they know to prepare everyone that, hey, that was like a little thing. We need to prepare for something big that's still going to happen. So pinpointing where exactly it happened is very important. In addition, shedding light on the structure of our inner planet also helps us to figure out how our Earth's magnetic field is created. And while that doesn't seem important either, maybe, figuring out how the Earth's magnetic field is created is very important because the Earth's magnetic field actually shields us from most of the harmful rays from the sun, as well as a lot of just harmful stuff that's coming from outer space. So a lot of that stuff doesn't seem important to us maybe in our day-to-day life, but it actually is very important. All right, so let's keep going. Seismic waves are vibrations in the ground. These can be generated by a number of phenomena, including earthquakes, underground explosions, landslides, or collapsing tunnels inside a mine. There are 4 major types of seismic waves, and each typically travels at different rates of speed. That's one big reason why scientists are able to tell them apart. If the waves arrived at vibration detecting instruments, which are called seismometers, at the same time, it would be difficult to tell them apart, which makes sense. So they tell them apart because they get to the measuring devices at different times, because they move at different speeds. Another major difference between these types of waves is how a material will move as the wave passes through it. With these differences in mind, let's review the major types of seismic waves. So 2 ways to tell them apart. If the scientist is sitting at a seismometer, they can look at the screen or look at the readout and say, okay, on the readout, you can look at the readout and the different times that the waves got to the machine, you can tell the different types of waves. If they're not sitting at the machine, then they can look at the material. Like, in other words, if you're not sitting at the machine, but you are maybe at a building that the wave passed through, you can look at the type of the type of damage that was done, and the different types of damage that was done by the different types of wave tells you what type of wave passed through. All right, so let's look at the different types of waves. So P versus S waves, and these are the most commonly known waves. Seismologists are scientists who study earthquakes. So we already talked about that. They also study how a quake's energy spreads through Earth's crust, as well as the deeper layers of our planet. The fastest seismic waves are known as P waves. That P stands for primary. Primary means first, so fastest, first. And early seismologists called them that because these waves were the first to arrive at seismometers from some distant quake. At Earth's surface, P waves travel somewhere between 5 and 8 kilometers per second, or 3.1 and 5 miles per second. I know that doesn't sound fast, but it's faster than the other ones. Deeper within the planet, where pressures are higher and material is typically more dense, these waves can travel up to 13 kilometers per second, or 8.1 miles per second. I'm going to scroll down a little bit. P waves travel through rock the same way that sound waves travel through air. That is, they move as pressure waves. Some people remember P waves are pressure waves. It technically stands for primary, but some people remember that too. When a pressure wave passes a certain point, the material it is passing through moves forward, then back, along the same path that the wave is traveling. P waves can travel through solids, liquids, and gases. That's one big difference between them and the other types of seismic waves, which typically travel only through solids, such as rock. Okay, so let's stop there. So P waves, number 1, travel through solids, liquids, and gases. The other ones usually only travel through solids. So that's actually very important. P waves travel through everything. So they can travel through magma. The other ones usually only travel through solids. So the other thing about P waves is that when they travel through something, the stuff that they travel through, solid, liquid, or gas, whatever, it moves forward and then back. So whatever it's traveling through vibrates like this. So what happens to a building when it does this? Buildings aren't usually made to do this and stay standing. So P waves can be kind of devastating to a building because if a building's foundation does this, not good. So in places that have a lot of earthquakes, buildings are usually made, like their foundations are usually made to withstand doing this. So there are structural things in place so that if their foundations do that, they don't fall over, or at least they're less likely to fall over. All right, so let's look at the second fastest type of seismic waves are secondary. So they get their second. They earned that name because they are typically the second set to reach seismometers from a distant quake. Not surprisingly, they're known as S waves. In general, S waves are only 60% as fast as P waves. So, along Earth's surface, they move at speeds of between 3 and 4.8 kilometers per second, or 1.9 and 3 miles per second. I know that's not that fast, but again, they get their second. As an S wave passes through a material, the site of its passing moves from side to side or up and down, as compared to the direction of wave traveling. This is why S waves are known as transverse waves. Transverse comes from the Latin words for turned across. S waves cannot travel through liquids or gases. That's because the types of stresses set by those waves can only be transmitted through solid materials. Okay, so let's stop there for a second. So P waves make things, as they travel this way, they make things do this. We talked about that, right? Sound waves, we talked about sound waves. We talked about longitudinal waves. That's what P waves are. As P waves go this way, the things they pass through do this. That's what longitudinal waves do. Remember, we talked about this in physics. And S waves are transverse waves, which we also talked about in physics. So as an S wave goes this way, the things they go through do this. So again, imagine a building. The P wave passes, and the building does this. Then, a couple seconds later, the S wave passes this way, and the building does this. So now, the building has just done this, and then a couple seconds later, it does this. Again, that building, if it's not properly made to do those things, not going to stand up for very long. That's why in earthquake-prone areas like LA, buildings are specially built. There are earthquake-safe buildings, and there are building codes in place to make those buildings safe. Now, I mean, for an earthquake that's crazy strong, things are going to fall over. But there are building codes in place to make things safe. All right, so let's keep going. Distinguishing earthquakes from nuclear shakes. Because P waves and S waves travel through Earth, not just along its surface, they're known as body waves. This trait makes them useful in a number of ways. For one, scientists can use P waves and S waves to identify where an earthquake began. To do that, they need to have data gathered by seismic instruments at 3 or more different locations. That lets them triangulate to find the source of Earth's shimmying. So what they can do is, let's say they have a station here, and a station over there. What they can do is they can say, okay, so the P wave got here, the P wave got here, and the P wave got here at these times. Okay, so we can figure out that if it got here, here, and here at these times, all right, we know they travel this fast through this type of rock. Then if they travel this fast through this type of rock, we know that the earthquake originated over there. The reason they can figure that out is because they know it travels this fast and it got to those stations at these times. It's literally the physics that we learned. They don't do anything more complicated than that. It's the physics that we learned. They do the velocity equation that we learned way back when. So they're doing what we learned. They're just doing it with the data they collect from their machines. All right. Triangulation is only possible when there are accurate measurements of the times at which P waves and S waves show up at each seismometer. Some techniques use only the P waves. Others also consider the time difference between the arrival of the first P waves and S waves. The farther the distance between the seismometer and the source of the quake, the more exaggerated that time difference will be. Which makes sense, because if S waves are slower, then if the earthquake is really far away, the S wave will lag behind the P wave by more time. Whatever method is used, it gives scientists only an estimate of how far from a seismometer the earthquake's source happens to be. So with a seismometer as a center, scientists draw a circle of the proper size on a map. But using only one seismometer, there's no way to tell in which direction the source was. It could be anywhere along the outer edge of that circle. By plotting the circles for at least 3 instruments on the same map, however, there will be a single point where those circles overlap. That marks the point on Earth's surface above the quake site. Most quakes occur deep within Earth's crust. The point where a quake originates is called its hypocenter. The point on Earth's surface directly above the hypocenter is called the quake's epicenter. So what they're saying is, basically, the spot inside the crust where those plates are catching is the hypocenter, and the place on top of the crust is the epicenter. But scientists don't just use these waves to map earthquakes. Those same seismic waves can also be generated by underground explosions. These might arise from a small blast inside an underground coal mine, for example. Or they might signal the test detonation of a nuclear weapon, such as several that recently took place in North Korea. And P waves, in particular, can strongly point to whether the seismic waves come from a natural quake or an unnatural blast. Here's why. When a natural earthquake occurs, one side of a fault zone slides in one direction. The other side slides in the opposite way. Doesn't that make sense? Transform boundary. They go like this. So one slides this way, one slides that way. So in a natural earthquake, one would slide that way, one would slide that way. So you'd see that. So a fault zone is a fracture in Earth's crust or a boundary between two tectonic plates, oh, we know that, where slippage can occur and seismic energy can be released. Now imagine that an earthquake occurs in an area that's covered with a network of seismometers. For some of the instruments, the first P waves to arrive will be a push from the quake, but for others, the first P waves to arrive will be a pull, one from one side of the tectonic plates, one from the other. For seismic vibrations generated by an unnatural explosion, the first P wave to arrive at every seismometer will provide a push, because from an explosion they would all be going out, right? Out from the blast. Not only that, the P waves generated by an unnatural explosion are typically sharp and sudden, so they die away pretty quickly, right? Because from an explosion they would all come like really fast. The vibrations produced by a natural earthquake instead tend to rumble for quite a while. That's because the slippage along fault zones in a natural quake doesn't happen all at once, like an explosion does. Because for a transform boundary, again, they kind of push, they push, they push. So we're getting like little bit of waves, little bit of waves, little bit of waves, and then they're still kind of, even after they still rumble, like, so you get a little bit of waves, little bit of waves, a lot of waves, a little bit of waves. So they rumble away for a while. Okay, still more flavors of seismic waves. At first, all of the quake's energy travels from its source deep within the planet as P waves and S waves. But when that energy reaches the surface, it now can spread as either of two different types of waves. Think of a quake's energy as a bubble rising from the bottom of a pond. The surface waves are much like the ripples in the pond's surface. Here, the waves spread from the quake's epicenter. Remember, that's the spot on top of the crust from where the quake occurs. These waves also are typically larger and cause much more damage than P waves and S waves. So that's kind of crazy because remember, the P waves and S waves they're causing some damage. The faster of these waves was named after British mathematician A.E.H. Love. More than 100 years ago, he worked out the math that explains how such waves move. The second type of surface waves were named for a British physicist who in the 1880s predicted their existence. This scientist was named John William Strutt. His father had been a British noble dubbed Lord Raleigh. At his father's death in the 1870s, Strutt inherited the title, becoming the next Lord Raleigh. The waves he predicted are now known as Raleigh waves. Of these two surface waves, the Love type travels a bit faster. Like S waves, Love waves shake the ground from side to side, so side to side. Oh, sorry. Compared to the direction they're headed. In other words, for a Love wave traveling north, the ground shakes back and forth from east to west. So if the wave's traveling towards you, then the ground shakes left to right. Raleigh waves, on the other hand, cause ground movements in two directions at once. So Raleigh waves are like, whoa, crazy. One of these motions is up and down, very much like waves on the ocean's surface. The other is a push-pull movement along the same path that the wave is traveling. So remember, that's what P waves do. Together, those motions generate a rolling action that can cause extreme damage to buildings and other structures. So in other words, Raleigh waves, what they do is they do this and this at the same time, and this at the same time end up doing this, which this to buildings, lots of damage. Okay, let's wind this up. Other uses for seismic waves. Geoscientists often use seismic waves to map details of the inner structure of our planet. For instance, the time it takes P waves and S waves to travel down into Earth and then return to the surface helps scientists calculate how deep the boundaries of Earth's major layers are. Remember, we talked about that when we talked about the Earth's layers. Those calculations are made possible in large part because researchers have measured the speed of seismic waves through rocks under immense pressure in the lab. P waves and S waves tell scientists a lot more than the depth ranges of Earth's major layers. In some cases, they also provide strong clues about the type and density of materials in those layers. For example, at distances of between 11,570 and 15,570 kilometers, or 7,190 to 9,670 miles from a major earthquake, seismometers don't record any S waves coming directly from that quake. That's a big clue that Earth's outer core is made of liquid, scientists say. In areas more than 15,570 kilometers away from a quake's epicenter, seismometers do detect S waves. Those waves develop from the energy of P waves that have traveled from Earth's outer core once again, enter the mostly solid mantle. That's the very thick layer that lies between Earth's outer core and its crust. At shallow depths in Earth's crust, all types of seismic waves can be used to map out relatively small geological structures. These include things such as faults and sediment-filled basins. Sediment-filled basins are broad bowls of solid rock where loose material accumulates. Such areas can be especially affected by earthquakes, which would make sense, because if you've got like a loose bunch of rock and an earthquake happens, it's going to be shaken up. That's because seismic waves can get trapped and bounce around inside that basin, making the sediment shake like jelly in a bowl. Again, the time it takes for a seismic wave to travel to a structure and then echo back helps scientists estimate how far away that structure is. Even people setting off small explosions of dynamite can trigger seismic waves. That means these can be mapped from afar. It's also possible to use data gathered by seismometers over a long period of time. Although such signals may be faint, they can be assembled into stronger signals, much in the same way that photographers can take photos in dim light by leaving their camera shutter open for minutes or even hours at a time. Okay, so that's the end of our 2 articles, and I hope that we've sort of remembered a little bit from physics about waves, and we've brought in a little bit of chemistry, so we're kind of combining our units here. Now, what I want us to do is I want us to go to the classwork section and look at the question sheet that goes along with these 2 articles. We're going to answer the questions, and then we're going to be done for the day. I apologize for not posting this yesterday. I'm very frustrated with everything yesterday, but we do have it for today. So thank you for watching, and have a good weekend. I will see you on Monday. All right? Bye, guys.